we're going to start right here at the engine. So the engines arrive, they come in, and they come in a can. So just really quickly, what's one of the biggest benefits of an Aero derivative or an LM6000? This can is designed to fit through the side door or main door of a 747. So you can drop ship an engine by air anywhere in the world based on this can design and how it comes together. So one of the key elements of an LM6000. So the LM6000 itself is an Aero derivative. It comes from the Aero source, so the core part of the engine in the middle, so that's basically from here to about here, is the CF680C2 or the equivalent. And if you've been on a 767 or 747, then you've flown with this engine on the wing. In addition to that, just for round figures, it's probably well over 90% of the engines flying on wing while you were flying were overhauled, because they don't stay new very long in the aerospace industry, in the aviation industry. So most likely you flew with an overhauled engine, overhauled by almost the exact same procedures here as you'd see in the aviation. Big difference is we're not an FAA certified shop, but otherwise there's only so many ways to take an engine apart and put it back together. There are some key things that I'll show you that we do differently, okay? So you've got the variable stator vanes in our high pressure compressor, then you've got the combustor, the high pressure turbine. The combustor, of course, has to have the change for the gas or liquid fuel, right? So we have a different nozzle system. Then we add the low pressure compressor on the front, the low pressure turbine on the back. What's unique about the LM6000 from an aeroderivative standpoint is those two are connected by a shaft, right? So in most aeroderivatives, it's a free power turbine. Free power turbines have certain benefits, but they also have drawbacks. One of the drawbacks is you must hot end drive if you have a free power turbine. Because we have a single shaft through the center, we can cold end drive. Cold end drive means we can axial exhaust, have a higher efficiency, simpler exhaust, which provides a long-term benefit to a power plant. So that's a critical element of a difference between the two. It makes it a very unique industrial engine from that standpoint. The reason I took the time to go through some of that is because the way we look at an engine is modular. So an LM6000 is a modular engine. We have a low pressure compressor, we have the high pressure compressor, the combustor, the high pressure turbine, and the low pressure turbine. Each of those modules can come apart. They can come apart in the field or in the shop, and that individual module can be replaced. Within that module, we can replace the individual parts. So if you look at the frame world, which I've been a part of in the past, generally speaking, most of those frames have a large major shaft. Now, yes, there are some components that can be changed in that, but that shaft runs and has a life over the duration of its usage. The aeroderivatives have the advantage that you can change almost every one of the parts within the module and continue the operation of that machine. You can revive it many times, and you don't have to worry about the rotor life issues that you sometimes see in the frame world. So it's another benefit of the aeroderivative. They are a little bit more complicated. It is a little bit more like driving a Ferrari than it is driving a Chevette. The maintenance has a little bit tighter requirements on it, and so it's very important how we deal with it in the shop. Okay, so just from an overview standpoint, the engine itself arrives like this. It arrives in a can. We remove the lid. The machine comes out, and we place it on a stand. We then tear it down into its individual modules. During that process, all of the parts are loaded in our electronic system, our MRO system, which tracks all the parts so that we can keep track of all the parts from your engine, or we can move those parts into inventory and build an engine out of inventory. It's whichever is the preferred path. But it allows us to track all the individual parts from each engine. Each of those parts then goes to one of three places. It either goes to an outside supplier for some repair, it goes to our own repair shop, or it goes to the warehouse in the kitting area. And our warehouse has 10 kitting areas for engines, which we set up and can control the parts in for each of the 10 engines. In addition to that, we can have anywhere from roughly 4 to 6 engines on the floor here, plus another couple of engines on the floor in our Houston service shop. So this is a level 4 shop. That means it's a complete teardown shop, down to every nut and bolt. There's only 4 others really roughly in the world. GE has 1 or 2, IHI has 1, MTU has 1, and TCT does. All of those companies are affiliated with GE. we are the only truly fully independent service shop in the world that's a level 4 LM6000 shop. When you talk about connecting the LPC to the LPT all the way through the engine, remember that the low pressure shaft turns at 3600 RPM. It turns at that RPM because that happens to be 60 hertz 2-pole generator speed, right? So you want to hold the low pressure shaft to that speed. The high pressure shaft, or the core from the aircraft engine, actually runs around this shaft, and its operating speed is above 10,000 RPM. It's probably between 10,200, 10,500 RPM is normal sort of speed for it. That is one of the big efficiency advantages of the LM6000. It also is an operability. Separating those two shafts and allowing them to operate at two different speeds means that the machine is more operable. It can move megawatt power faster, right? It can respond quicker to, let's say, the throttle, for lack of a better term, and that enables the machine to perform better for a customer from a standpoint of, let's say, ancillary services, right? Load following, the loading, load ramp for the machine, and even the start time, right? It's all benefit of that shaft design. So the engine comes from the cans. It locates itself onto our stands. You'll see our stands are a little different. The carts that are behind you are mobile carts. They stand up. One of the things that we did when we re-looked at how we did our work here at PROENERGY was that we went down to the individual employee level and we said, what could we do to make it better, right? How do we make your day better? How do we make you more productive? And looking heavily at safety. We talked about safety at the beginning of the tour. Safety was a big thing. So when you're working on the road movable stand, it's convenient because you can move the stand around, but you're up high. So you're climbing on the stand, you're working, in a place where you could fall, you could twist your ankle, there's things like that. We've moved our stands down lower. Now this means occasionally somebody has to work on their knees because they're down on the bottom and below. So that's a choice. But we made one of the stands and we said, okay, we're going to use this stand. We trialed it for a while, and then I said, I'm going to get you two new stands. Which ones do you want? And you can see we have multiple stands of the two design. So the way we look at it and the way we look at things here in the shop is that if it drives safety for our employees, that delivers productivity. If someone feels more safe and more comfortable doing something, they can normally do it more productively. And so that's just a fundamental philosophy of who we are, right? That productivity and safety connection. Because as we zoned in and we did our 5S Kaizens on all the shops, focusing in on the 2500 and 6000, what we saw in terms of productivity ranged from shop to shop between 25 to 50%. So we took between 25 and 50% of the hours out of the work, and we're able to achieve the same or a higher level of quality with better safety for the employees. So it's for us a big accomplishment for the shops in how we built our shops and worked. So the machines come down. You can see a machine here that's already partially down. It only takes a few days to get the machine into modules. It takes roughly a week or so to get the externals off and all tagged and placed and everything. And then the machine starts to come down. You can see the LPT module is off this machine. And once the modules come off, they go to the different stations in the shop. So for example, right behind us is the high pressure turbine, or the high pressure compressor, I'm sorry. So you can see the high pressure compressor stator. So this will come down depending on the level of work scope. So a customer may want a full overhaul, or it may be what we refer to as a hospital visit. We'd take this down. If we take it down completely, every part comes off it all gets cleaned, inspected. We'll get to that in the other building, right? But when we think about both tearing it down and building it up, there's three things that are key to any gas turbine, right? Number one is materials. Getting the materials right, getting the repairs right, getting your coatings right. The joke from an engineering standpoint has always been that designing a gas turbine is like designing a fireplace out of wax. So wax obviously melts when you have a fire next to it. All of the metals in the hot section of the gas turbine are operating above their melting point. The reason they can do that is because they have air cooling, they have coatings on them, so we control very carefully how the air flows across the airfoils and what materials you use, what coatings you use to make sure that they survive that extreme environment. So that's number one. Most of that will be over at the repair shop or in the original design. In the depot, the other two things which are critical are clearances. So clearances give you your performance. If your tip is very close to the casing, then you don't have a lot of leakage flow and you're going to get a strong performing engine. If the other is vibration, right? What's wonderful about a turbine is it has very few, moving parts. In a big frame it's one, and the aeroderivative you got two rotors, they're both turning. There are other moving parts, but the majority of the major moving parts are two rotors. So if you get those two rotors balanced well, they run very clean and they'll run for a long time. And on top of that, if they're not vibrating, your clearances are better as well, right? So this shop is all about getting the clearances right and making sure everything's balanced, aligned, the drop checks are in place, everything is positioned the way it needs to. If you do that, then you're going to have a strong operating machine. So part of that is you'll see this is vertical. This in this case, vertical is for a convenience. But right behind us, you can see an engine being vertically assembled. So what's important about an engine being vertically assembled is that you do not want to assemble it horizontally. You will get a certain amount of bow. It's a small amount of bow, but you can control that with jacking and with other techniques. But the best way to assemble the engine is vertically, right? That ensures that you're well laid out from a balance standpoint, concentric and concentric between the two parts. So the stator part and the rotor part come together here. We do wax checks, we do clearance checks, and make sure that we have a strong clearance in the machine as we assemble it. This is a home developed tooling setup. We really like the multiple platforms, having it off the floor, so we have a nice high working height off the floor, as well as the railing and the high working height above. You'll see a shadow board up there, and you'll see shadow boards through all the shops. We got rid of all our toolboxes, or the majority of them. We have a few small ones, but they're now off shadow boards. Those shadow boards contain the tools you need and are a big part of our visual management. So we manage the shops visually. You'll see we don't have tons and tons of metrics around this operation took 0.3 seconds because we're not building 10,000 widgets. Right? We're building 30 engines or 40 engines. So what's most important is to know where things are, how they're moving through the shop, and that'll give you the understanding of whether you're on time or behind. And then knowing the shadow boards tells you whether your tools are in use, not in use, or potentially need repair or replacement. Okay? All right, so that's the compressor stator. So as we look at the rotor area, one of the big things is clearance. So we have a high pressure turbine rotor right over here on our grinding machine. So the grinding machine is our own machine, it's homegrown. We developed it, we put an Allen Bradley control system on it. It's actually the same control system that we use for controlling our gas turbines. And we do that in order to hold very tight tolerances on the tip grind for the HPT. The HPT rotor is obviously where you get the bulk of your output. You still get a lot of output from the LPT, but your highest output comes from the HPT. So you can see the stage 1 and 2 blades. We tip grind those blades to a very tight tolerance, and then at the same time we have a CNC machine for grinding our shrouds. So we can control the shroud grind and the tip grind on the blades and match those grinds to control the clearance extremely tightly on the machines. And that tight tolerance between the blades and the shrouds is critical to our performance. So, I've been asked in the past things about the tip grind. I would tell you this. So one of the reasons we are so focused on tip grind and why it's so important to us is very simple. We always want to make performance. So does everyone else. But if you're the OEM and you don't make performance, they say, okay, well, they'll fix it. When you're a third-party independent shop and you don't make performance, people say, I told you so, right? And we don't want to hear that. So we're very dedicated, very focused on making sure that our clearances are right to make our performance the first time every time. So the turbine rotor assembly area has a platform on it which allows us to hold concentric, to allow us to build it in a flat mode, to be able to build the wheels up. Before you build the wheels up, actually we want to balance them. So right behind you we have what we refer to sometimes as the mushroom. You can probably understand why we'd call that a mushroom. But that's our static balance machine. So we balance all of our major components statically, and we do it with and without the blades. By patterning the blades and patterning the wheels, we can minimize the amount of balance adjustments that's required dynamically. So we do all of our major components here, then we build the rotors. Then after the rotor builds, we do the grinds. From the grind, we go to a dynamic balance. So the dynamic balance machine allows you to get, between about 600 and about 1600 RPM, depending on the area of the machine that needs to be balanced. We dynamically balance it. The LM6000 has been designed and by the OEM in a very effective manner that we balance each of the modules. And if the modules are balanced properly, when you build the engine, there should be no need to balance the engine as a total unit. Now that said, machines go to site, they get hooked up to the generator, there's a load coupling, there's alignment, so sometimes, there is a balance shot in the field. But as a general rule, the engine rarely needs any sort of field balancing, because when you put those fully balanced modules together, you get a very strong component. Okay? As we look over here, you'll see some of the stator. So this is where stage 1, and then we can see the stage 2 nozzle assembly. So the stage 2 nozzle assembly is a good example of one of the ways we do things a little differently. So these shrouds have been ground, as I mentioned, on the CNC to match the blade tip requirements. The nozzles themselves are built out in that, and what we do is we use a slave set of nozzles. So often in the tip grinding, it'll be your actual nozzles in the grind, and then you flow fluid or something through them to keep the debris out of that stage 2 nozzle. Rather than doing that, we actually use a slave set of nozzles, and that way when we're grinding, we can remove that slave set of nozzles and have no concern about any debris getting into the brand new nozzles going into the new build. And that ensures a good, clean build. Then we can replace those, build that out. And this is a stage 2 nozzle. This is a good module. This is a good place. We also do rotables, so some of these will be done for an individual engine. In other cases, we'll build this out as a rotable. So we'll have a rotable hot section, and what that means is if you need a hot section changed in the field, or if you just want to come into the shop and get a high turnaround time, then we can use a rotable. We can open your engine up, change out the hot section with one that's already on the shelf, and then return the engine. And we can get engine overhaul returns, with rotables in 30 days sometimes, or even less. For a full overhaul, our standard cycle is 120 days. We can sometimes beat that depending on the scope of the overhaul. That's a full major, but that's roughly where we're at. As I mentioned, we can get about 4 to 6 machines in here. We had 9 in here once. They were all hospital visits, but we can get 4 to 6 machines in WIP plus the 10 slots in the warehouse, so we can actively have as many as 10 to 16 engines in WIP all at the same time, and which would allow us to do those builds. And we really haven't been fully tested from a capacity standpoint, but as I mentioned, last year we did about the equivalent of about 30 overhauls, and our target for this year is about the equivalent of 38. When I say equivalent, you have to throw in the rotables and the hospital visits and estimate those hours versus a major. But that's roughly what we did last year. We did many more than 30 engines because of all the hospital visits, but it was the equivalent, let's say, of 30 overhauls. Compressor rotor goes together very similar. The high pressure compressor rotor, very similar to the high pressure turbine. It's on a stand. The stand levels it out. It enables you to make sure everything's concentric and that you can build. So we build the high pressure turbine. It all gets bladed here in this part of the facility. And then similar to the high pressure turbine, the high pressure compressor rotor would go back to our grinding machine on the high pressure compressor rotor. For the high pressure compressor rotor, the angle of the tip is very important. As the air flows through the machine, it narrows down, and you want to make sure that you've got the right angle on that tip because as the blade moves back and forth, if you cut it straight and it moved back and forth, you'd have a big leakage. If it's cut at the right angle, it moves back and forth. It controls that leakage to a much lower level, and it enables the machine to run, to have a tight tolerance, but not pinch on start, which is what you want to avoid. Okay? Here's an example of how we operate in the shop. This is a consumable kit. So as everything comes out of the warehouse, it comes with all of the parts, but it also would come with a consumable kit. So each of these consumable kits is set up based on exactly what parts are required for the operation. So for each operation, it comes with the exact parts, the parts counted out, right? And this is this kit. So this kit is a 2-drawer kit. Some of the kits, you can probably see a blue one down there near the end of the aisle, which is almost a stand-up toolbox. Bigger parts, more parts. But this is all counted out by our kitting team. It all comes as a full set. And then when it returns to the warehouse, it's scanned for what's missing. And that's how we determine what parts were used on a build. Whatever we have to replace is what was actually used on the build, right? And it allows us to track our parts, know exactly what's there, and it's a very reliable way to know how the build came together. So this kitting process, and we do that for each of the operations on the shop floor here. So actually one of the new features is in the air. As we looked at safety, we had people that were working up on top of the LPT and the turbine rear frame, and we were having to tie them off, or they were having to be on stands. So one of the things we built was a simple platform. So we built a number of platforms. You can see some of the tooling at the back of the shop. Each of those platforms were built with, again, safety and productivity in mind. We built a whole new LPT area. At the end of the bench, you'll see a toolbox. So in that toolbox, we go under the philosophy of how you would build a turbine in the military, or on the deck of a carrier, let's say. On the deck of a carrier, you have to know where every single tool is. You cannot allow a tool to be on the floor or in any way end up in the engine. So that toolbox has the foam pads in it, and it has every tool required for that operation and not a single more. So there's no full set of wrenches. There's only the wrenches that are required to do the operation. There's only the sockets that are required to do the operation. So that's set up in those toolboxes, and when the operation's done, everything has to be there, right? That way we know, and we can control our tools and replace the ones that get damaged easily. But those toolboxes are very critical to how we operate. Okay? And then, as I mentioned from here, the other thing is, here all the parts go to one of 3 areas. Although we do send some work to outside vendors, one of our big partners, as you probably know, is Chromalloy. Chromalloy we buy hot gas path parts, especially the high pressure parts from. They also do some repair work for us. But unlike most of the overhaul shops in the world, our overhaul shop has a full repair and new make shop right across the road. So our repair engineers, our new make engineers and design engineers all support the depot, and they're able to come over. If we see something unusual, we see something unexpected, or we want to trial a repair, or we want to trial a fit, we can do it right here. And the teams can interact directly, which to me is an enormous advantage for us. It's been extremely helpful in our build-out, problem-solving, RCA execution. In addition to that, myself, I sit just around the corner. I love to sit in the shop. If it's not noisy and I don't smell a little bit like cutting fluid, something's probably wrong. My Vice President of Engineering was a materials chief engineer at General Electric, Paul Damasio. He's worked in gas turbines for a large part of his career. He was at GE for, I think, almost 30 years. And so between the two of us, we're generally the top-level sign-off. We also have a core engineering team, our new Director of Gas Turbine Engineering, Hai Sam, and we have our equivalent manager of our packaging engineering, Kevin Chow. So those guys are directly supportive not only of the shops and the shop execution, but product development. And for your machines, we're also involved in the fleet support. So when there's a fleet issue, an issue with a machine in the field, that information comes to us for our evaluation and support as well. So that's how we're structured for that.